Hello. Testing. What? Okay. Why? What? Why? 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 今天要上价值。Well, let me wait for a minute for everyone to come here first. Ah, what?要开课了，然后要开课。
What's the question? Can I use, because I already did this, can I use this hint?
Yeah.
I can.
I mean, you need to show this.
Oh, I know I need to do this.
Yeah.
I want to do this.
For the definition, yeah. By definition. Okay, and ready? Ready. Okay, before we start, right? I think we should discuss about how you learn a subject. Okay, how you learn a subject. So I picked from this Chinese philosophy. Okay, this is what I'm practicing. So the Chinese philosophy is about looking at a mountain. Okay, looking at a hill. Okay, the original phrase is 看山是山，看山不是山，看山还是山。Okay, so in English, what is it? So I break into 4 parts here. So first, you don't know this is a mountain. Okay, when you see a new subject, you don't know what is it. Okay. Second, you learn that it is a mountain. Okay. But third, you should doubt that is it really a mountain. Okay. And then fourth, you realize that it is a mountain. Okay. So typically people will stop at the second stage. You are happy. I think I know it. Okay, this is the mountain. Okay. But you should really think deeper whether is this a mountain. Okay. And then finally you explore all the possibilities. Okay. And then finally you still think that it is a mountain. So I hope you can practice this. So never stop acquiring knowledge. Okay. Yeah. In your life. Yeah. Okay. So don't stop acquiring knowledge in your life. Okay. So similarly, what is directional derivative? Okay. Last time we learned that what is directional derivative, right? So we learned that when is it this directional derivative maximized? When it is in the direction of gradient. Okay. Why is it in the direction of gradient? You pick when it is maximized. So what's the real life? I mean, how you experience or how you feel this maximized gradient, right? So this is happening in everyday life. Okay, when you walk down the slope, okay, what's the slopest way to walk down the slope? Huh? You just follow the slope and go down. You will reach the maximum speed, right? Is that right? Is that right? Okay. So to avoid the slopest slope, how do? You can work sideways first. Okay, see this picture here. Yeah, instead of just walking down this hill straight, you can walk sideways, right? You feel better. So if the old man have a knee problems, right? So you should tell the person to walk sideways. Right. So this reduce the impact of the heel to the body. Right? Is that right? You never experienced this, is it? You try, okay? I ask you to try. So try to walk on the staircase, okay? See which one is most tired. You walk straight up the staircase or you walk sideways to the staircase. You try yourself. See which one you feel more tired. Okay? So you try. One is you walk straight up the staircase. The other one is you walk sideways up the staircase. You see which one you feel more tired. You can try it yourself after the class. Okay, you try it. Okay. So my argument is if you go sideways, okay, you will feel less tired because you are not against the slope. Okay, you reduce the impact of the slope. Okay, so this is calculated using the dot product here. Show you that the gradient is smaller if you walk against the direction of your gradient. Okay, gradient of your surface. Is that okay? About this maximizing directional derivative. Yeah, you try in your real life. Okay. Yeah. Because the other class keep asking me what's the U, what's the U, what's the U. Yeah. So what's the U? The U is the direction that you pick. Okay. Gradient of F is the one that defined by your surface. Okay. Yeah. You feel a bit hot today. The echo is not working. Yeah. Yeah. Okay. This one we have gone through before. Okay, so this one we've gone through before, right? What's the idea between these two? Okay, let me just pick out the thing I want to say first, and then I show you this picture here. So there are two main subjects here. I hope you already gone through this, some of the definition. So I'll just start with these two. Okay, what is this two? Okay, what is this two? What's these two things here? Okay. On the left-hand side, what is this? This is a function of two variables. Function of two variables. The left-hand side is what? Function of three variables. Okay, three variables. But you make an equation out of it. Okay, so meaning you cut it. Okay, so you cut the object. So cut what object? Okay, cut the function. Cut the function w equals to f x y z. Okay, we cut the function at w equals to k. Okay, so see here. Okay, here is a three variable function. Here is a two variable function. So last time what I say, so if you have two variable function, this means what? I tell you how a piece of paper sitting inside the R3. How about three variable? The graph of three variable function live in where? R3 plus R. So R4. Okay. So this is a three-dimensional object sitting in R4. Okay. But we cut it. Okay. After we cut it, we cut one dimension down. So what I left with is two-dimensional. Okay. So these two, the similar things between these two is you get two-dimensional object. Okay. Now cannot see. Why two, why not three? Okay. So first of all, are you happy that we have a two-dimensional object in three dimension for the left-hand side? Do you agree with this? So this give a graph of f in R3. Agree? This part agree, right? Okay. So how about the left hand side? Okay. Yeah, left hand side. So left hand side is what? Left hand side, if you look at the graph of f, okay, graph of f live in where? R4. Okay. But this is a three-dimensional object here. Three-dimension, right? Because I only fit in x, y, z, controlled by x, y, z. Okay. On the left-hand side, controlled by x, y, two-dimensional. Two-dimensional sitting. Okay, so let me write down. So two-dimensional graph sitting in R3. So you can see that all of them are one-dimensional lower, exactly because the codomain you're using. Make sense? Okay. So so when I cut the three-dimensional using W equals to K. Okay, what do I get? I reduce one dimension, so I get two dimension. Okay, so how should you imagine this? So you can imagine from the lower dimensional as well. Okay, how you imagine this? So let's say we look at z equals to square root 1 minus x squared minus y squared. Okay, so anyone know what is this? This is a very important example. Okay, if you work out from this calculus tool, anything you don't remember, you must remember this. Okay, the positive hemisphere. Okay, the positive hemisphere. Okay, so let's say what's the level curve of this graph? Okay, so I look at 1 minus x squared minus y squared equal to 0. Okay, what's the level curve of this? What's the level curve of this? What's the level curve of this? It's just a circle, right? Circle is one-dimensional, right? Circle is one-dimensional, just a line. I mean, close line. Since you already learned close. Okay, it's a close line. Okay, so you reduce when you cut, you use the equation, you cut the function down by one dimension. Make sense or not? This is the what is this? This is the linear algebra, linear algebra. So let me show you the linear algebra. So for example, you want to solve this. Okay, you have two variable. I only tell you one equation. What does this give? You reduce R2 to just a line. What is this line here? Y equals to half x. Okay. If I give you two equations for two variable, okay, what can I do? What can I have? Let's say I pick x equals to, how about x equals to 4, okay? Let's say I pick both of them. Okay, I add two equations to two variable. What do I get? I get a solve the system of linear equation. What do you get? Huh? You get a dot. You get a point. Okay, so you see, two dimension. You put one equation, you reduce to a line. Put two equation, reduce to a dot. So you reduce dimension. So the dimension I'm referring to is you need to have this in your mind. So 0 dimension is a dot. Okay, 1 dimension is a line. Okay, 2 dimension is a surface. Okay, 3 dimension is a solid. Okay, if solid makes sense to you, right? So and so on, and keep going. So I mean, you study maths, right? Okay, you study maths. You should ask how to generalize this thing. Okay, how to generalize. So to study maths, okay, you need to know specific example. You need to able to generalize specific example. Okay, this is the two skill. When you see everything, you need to do it. Okay, because you study maths. Okay, so in this case here, maybe you need to ask me how I go from zero to one dimension, 1 to 2 dimension, 2 to 3 dimension, right? Because we need to know this to be able to generalize higher dimensional. Okay, so like what I say last time here. So how you go from 0 dimension to 1 dimension? Okay, you can think of it as a infinitely many dots putting together. Okay, how to go from 1 dimensional to 2 dimensional? You can think of it as a infinitely many lines putting together. Okay, 2 to 3, how? You can put infinitely many surface together. Okay, and then go on and on. Okay, this is one way of thinking of it. Okay, okay. So so what I present you is two ways of getting two-dimensional objects here. Okay, two ways of getting two-dimensional objects here. So so if you don't understand this, we should give you an example, okay, to illustrate this. How is it two ways to getting a two-dimensional objects here? So we go back to the same example, sphere. Okay, sphere and positive hemisphere. Next is abstract but concrete at the same time. Okay, why is it abstract? Because we want to mention all the concrete things together. That's why it becomes abstract. Okay, otherwise it has to be very really concrete. Okay, people must start with examples before they talk about ideas. Okay, otherwise the idea is bullshit. Okay, it's nonsense. Okay, must start from some example. So the example I start here is sphere. Okay, let's name this equation. So sphere and positive hemisphere. Okay, so if you want to compare to what I wrote here, you see, my capital Fxyz become this part here. Okay, and then my k become 1 in this case. On the left hand side here, z equal to some function. Here, z equal to the square root function here. Okay, so you should ask this k here. You should see this, right? You should immediately ask, can I move 1 to the other side or not? Because 0 is also a k. Okay, can I do that or not? Do they describe the same object or not? Yeah, you should immediately ask. Okay, you cannot answer, never mind, but at least you need to ask. Okay, so the answer is yes, because it's really the same equation. Later we will try and differentiate it. It also doesn't affect it. Okay. Okay, so what we trying to achieve here is we have these two objects. Okay, we have these two objects. Okay, the idea is if I look at the tangent plane, okay, tangent plane at this point, you know what this point is? What's that point? If I told you that this is a unique sphere. This point. Of course, can you give specific coordinate? 0, 0, 1. Why is it 0, 0, 1? Yes. Okay, I pick the highest point. Okay, and then this is centered at 0, 0. Okay. Also, you can see that 0, 0, only z equals to plus minus 1 satisfy this equation. Where's the minus 1? 0, 0 minus 1 is at the bottom. Okay, so I pick the top one. So let's say I pick a tangent plane on top of this. Okay. So the question is it the same if I just find the tangent plane on the positive hemisphere? Yeah, do you think it's the same or not? If I look at the whole sphere and then I take this highest point here, I take the tangent plane, and I ignore the negative part. I just look at the positive part and then find the tangent plane. Do you think it's the same or not? Same, right? Okay, it should be the same. Okay, this has been shown last time. Okay, so the normal normal tangent, normal line, tangent plane. Okay, on this side is so okay, let me write some notation here so that we have thing to use. Okay, so the normal line to the tangent plane, okay, on both sides, what do you have? Okay, on one side, if you note, you should recall from your definition, right? So I will write it down here, or you just take my word. So del F here is 2x, 2y, and 2z. Okay. How about for z equal to fxy? Do you remember what's the formula for normal line or not? On this case here. You remember or not? Or at least remember the formula for the tangent plane. Okay, if not, I also recall here. So it is this sorry, x minus x naught plus fy x naught y naught. Okay, which means what? Which means this is the normal vector. Okay, sorry, normal vector is better. So the normal vector here is del f over del x, del f over del y, and minus 1. Okay or not? Going from this plane equation to normal line. So you need to make this into plane equation first. Okay, and then you read the coefficient of your coordinate. Is it okay? Okay. Okay. So last time we spent some time proving this, right? Remember? Remember? Okay, maybe you don't remember the process, but do you remember we did this at least? Okay. Yeah. Okay. So this is what we did. So this is what we did. Okay. So in this case here, I'm going to show you these two are really the same thing using this example. Okay. So in this case here, what is del f del x? This is testing you. Can you do differentiation? 智勇 what is del f del x? 永志 sorry. Confused with the badminton player. Hi, 永志. You don't know? Okay. Do you know what you need to differentiate or not? Do you know what's the function you need to differentiate? Yeah, the square root function. So how do you differentiate a square root function? Partial differentiate the square root function. How to differentiate this? Hi, Huayin. How to differentiate this?
Chain rule.
Okay, good. So what do you get?
1 times 1 minus x squared minus y squared negative 1 over negative 1 over 2.
Okay.
And then do the inside one negative times negative 2x.
Okay. Okay, good. So let me rearrange it. Good, very good. Yeah, this is the chain rule. Okay, and then so on. And so what do you get? You will get similar term half time minus y of minus x squared minus y squared half and minus 1. Okay. So you ask, hey, how these two are the same? How these two the similar thing? Are they similar or not? Similar? Wow. Brian, why you think that they are similar? What is equal to x squared minus y squared? Okay, z. You mean you want to replace the denominator with z, is it? Okay, let's do that. Let's cancel out everything, and then we left with x over z, and then y minus y over z, and then minus 1. Okay? Okay, is this what you want? Okay, so the normal vector to the tangent plane on the same surface, one of them is given by this. The other one is given by this. Are they similar or not? Why? Are they similar? You want to continue, right? Huh? No? Okay, you see up to here. I think this is good. This is the first step you need to see it. So, are they similar or not? Yes. 本说, right? 本说. Okay, why are they similar? Yeah, okay. So, they are actually scalar multiple of each other. Right? So, this, then we'll get 2x, 2y, and 2z. Okay, so what you can see is at every point, okay, at every point, meaning I need to evaluate this z here. Okay, after I evaluate this z here, del f is a scalar multiple of this special normal vector here. Okay, so a plane is defined by the normal vector, the direction of the normal vector. Okay, so they define the same plane. Is it okay? Okay. Yeah. Yeah. Okay. Okay, so they define the same thing. Yeah. One half over 2z. Yeah, should be 1/2 over. Should be 1 over 2z. Yeah, should be 1 over 2z. Yeah. Thank you. Yeah. Okay. Yeah. Yeah. So my point is, there are two ways of getting the tangent plane using different equation, different function. Okay. The way you describe it. Okay, you see the way we describe this sphere, right? It's very interesting one. Okay. One of them is this, the whole thing here. The other one is we define it part by part. So how about the negative part? How about the negative part? Can you describe a negative part using just Z? What's the negative part? 七风啊. What's the negative part? How to define the negative negative hemisphere? The hint is here or here. You got square root, right? Mm-hmm. One plus. Everything under is negative, right? Just negative of the thing above, right? Okay. So you just put negative in front of your z. Okay. Okay. So in this way, you can cover the whole sphere just using this kind of condition. But the good way of using this this presentation here is you can do it all together. You can do it all together. But most of the time now, most of the technology now cannot deal with global thing. We deal with local thing. Okay.
So you want to improve the technology?
I hope. I hope.
Good.
Okay. Yeah. Okay. So there are two ideas here: locally or globally. Locally or globally. Okay. Yeah. Yeah. You also notice that actually the two function we see here, right, is different. Right. This two function is actually different. It's really different. Okay. This capital F here, right, is not a sphere actually. It's not a sphere. Okay. Only the level surface is a sphere. Okay. This thing is not a sphere. Yeah. But Z, how about Z here? This is a hemisphere. Yeah. So these are really two different things. Yeah. Because the other class asked me why the gradient are perpendicular to the tangent plane, right? Because in calculus, in one variable calculus, you see that the slope is give you the tangent line, right? Okay. But why in two-dimensional case they are perpendicular? Okay. This is because actually the function you look at is different. It's no longer the function of two variables. You are looking at the function of three variables, and then you get some information from there. Okay. And then how about the derivation, right? Last time we already showed it using the implicit. Okay. So last time we used the implicit differentiation to obtain a relation between tangent vector and the gradient. Okay. So I mean I can straight away show you here. So let's look at this. Okay. How about I give you one concrete example? I think otherwise you don't believe me. So I give you a concrete example, right? So the concrete example I'm going to give you is, let's look at a path that passed through 0, 0, 1. Okay, look at the path. So how you write down this path? In this class, did we do parametric curve or not? Have we done parametric curve?
Yes.
We done it, right? Okay. So let's look at this path here. So how we write down this parametric curve here? What's the way to write down this parametric curve? I mean, just a semicircle. Okay, we don't want to do fancy stuff. Just do semicircle. Okay, so path, semicircle path. How we write down this? Semicircle. Okay, how we parameterize this? Maybe I need to give you some axis, right? So let's do some axis. So let's let this path lies on x-axis. You want x-axis? Okay, so let's cut it. Okay, let's cut it. Let's look at the sphere when we look at the cross-sectional x and z. Okay, and then we look at this path here, sitting inside the curve. Make sense or not? Does it make sense? Make sense or not? If I draw this, if I pick this path out, does it make sense or not? Can make sense? Can make sense? What am I trying to do? Express the curve in polar coordinate. Okay. I mean, you can think of it that way. So I pick a specific path here. Okay, I pick a specific path here. Okay, and then I claim that this path should live on the surface on the sphere. Okay, how do you make sure this path live on the surface of the sphere? You need to make sure. So path is made out by what? Like just now what I said. Path is made out by what? Where is my dimension picture? Path is made out by what? Point. Okay, so you need to specify every point for me. Right. So all these points have to live inside my sphere. Okay, so that means all the coordinates have to satisfy the sphere equation here. Okay, so what is the parameterized curve I want to write down? Okay, I will write down cos t 0 sine t. Does this work? Okay, why I put 0 at y? Because this line lives on the y equals to 0 plane, right? Okay, and then why I put cos t and sine t here? Cos square plus sine square t equals to 1 when y equals 0. Okay, so I make sure that this curve here lives on the surface. Okay. Yeah, makes sense. Okay, so now let's look at the tangent vector at this point here. Okay, how to find tangent vector at that point? We need to do r t. Okay, we need to do r prime t. So let me move. So okay. While I'm moving this stuff, right, you should think about what is r prime t. What is r prime t? Huh? What is r prime t? A bit slow or differentiating cos t. Huh? Like minus sine t, 0, and cos t. Okay. So what's this point here? Okay, what's this point here? When t equals to what? What's this point here? When t equals to what? When is this number here 0, 0, 1? When is this vector 0, 0, 1? T equals to pi over 2. Okay, pi over 2, good. So our point that we are interested is when t equals to pi over 2. So this vector here is exactly 0, 0, 1. Okay, so when at pi over 2, what is your tangent? What's your tangent? Oh, a bit slow. Sine pi over 2. 1, but you got minus here, so minus 1 is it? Okay, minus 1, 0, and 0. Okay, good. So where is minus 1, 0, 0? Where's this vector here? So this is a x direction vector, okay, with minus 1 scalar. Okay, you have minus 1 go to the other side of your x. Okay, and then just now we claimed that this gradient vector is perpendicular to this tangent vector, right? Tangent plane, everything in tangent plane, in particular this one. Okay, so let's compute what is delta f at this point, at the point 0, 0, 1. What is it? You get 0, 0, 2. Okay, where is 0, 0, 2? Is the vertical vector from origin, okay, with the scalar 2. The stupid thing. So this one is 1, 0. Okay, so let me ask you a question. Is minus 0, 0, perpendicular to 0, 0, 2. You still remember how to check whether they are perpendicular? If the dot product is equal to 0. Okay. Actually, I included this example in your lecture notes. I'm not sure you read it or not. You read it. Yeah. Yeah, although I overspend my time again, but let me tell you, don't worry about my spending. Yeah, question. Yeah. Yeah. Gradient of f is perpendicular to the surface, the tangent plane. Yeah. Yeah. But I mean the gradient, right? Don't confuse with the gradient of the big F and small f. Please don't confuse because the other class they're confused. So don't confuse with this big gradient of big F and gradient as small f. Okay. For small f here, you need to add an extra -1 because small f only have 2-dimensional. Your tangent plane live in 3-dimensional. So your normal vector need to be 3-dimensional. Okay. I mean, this is one thing you need to take note. The gradient of what? Okay, gradient of what? Okay. Although this small f also give you gradient, but you need to take note of this -1. Sense or not? I mean, you can keep asking. Yeah, you can keep asking if you want. You confused with how to find the tangent plane.
If the gradient is at the point of the
Yes.
here,
Yes.
the gradient of
Yes. Yes. That's right. That's right. That's right. Yes. I'm trying to, yeah, this is the, yes. This is the confusion point from the other class as well. So where's this confusion coming from? This confusion coming from gradient of what is the, not, is perpendicular to the tangent plane. Gradient of what? Okay, there are two things here. There are two gradients here. Gradient of capital F and gradient of small f. Okay, these two have difference. You know, these two have difference here. Gradient of small f and gradient of capital F. These two have difference because small f and big F is different. Okay, but the surface that described is similar. I don't want to say the same. It's similar. Okay. This is the point there. Okay. Yeah, you can try think about it and then look at this example again. Okay. My key point here is gradient of what is the normal vector of our tangent plane. It's very important. More question? More question? Yeah.
this is the
Yeah, sure.
so you find gradient. So the gradient is a line
Yes.
touching the point on the top.
Yes. Yeah, so this is not the gradient that you understood, right? The gradient I'm talking about and the gradient you're talking about is different. Okay. My definition of gradient is this one. Okay. The thing that you talk about is actually derivative. It's the derivative that rotates. It's the derivative that rotates. The directional derivative. Gradient don't rotate. Gradient only have one vector. So we are talking a different things now, right? So the thing that you mentioned about the gradient is the directional derivative. It's the directional derivative that rotates. It's not the gradient. gradient only have one gradient, one vector at one point. You give me a single point, I give you a single gradient vector. Okay, the thing that rotates is the directional derivative. Okay, because that one is based on direction. You can put any u you like.
It's a concept. It's the gradient.
No, it's perpendicular to the tangent plane. Just now I already mentioned. It's perpendicular to the tangent plane. So it's definitely not on the tangent plane. Okay. Of course, it touched the point itself, right? Because it emanates from the point. Like, I mean, in this case here, you see, this is 0, 0, 1. So the gradient is 0, 0, 2 from this point. I mean, you can consider the whole line if you want, but yeah, anyway. Yeah, so this gradient line, the gradient is definitely not on the tangent plane because it is perpendicular to the tangent plane. Maybe I think you are confused with my example here, this gradient here. Okay. You mean the reason? You mean this reason? This reason? This is the reason. This is a specific example. We can draw a more general example, general statement using implicit differentiation. It is in your note. Okay. I mean, yeah, this is the reason. Yeah, this is the reason. Yeah, this is the reason. You can remember this example, and then why is it true? Use the implicit differentiation. Okay. Maybe you confuse with the directional derivative because I tell you that this is the gradient. Is it? Is it? Why is this a gradient? So this is a gradient of small f. This is a small f. Okay. Small f tells you that if you walk this direction, it is the steepest. You mean that you see, small f here give you a vector in 2 dimensions. Okay. Small f, gradient of small f give you 2-dimensional vector here. Okay. It tells you which direction is the steepest. Okay. It doesn't tell you the normal line yet. But when you add on this extra number -1, it becomes the normal line to that tangent thing. I mean, I try to point out one possible confusion point. At least that's what I get from discussion with the other class. Does it better? Do you feel better? Not better? Confused Ziqian some more. No question? No question. Don't want to ask. Question? Yeah, I mean, maybe you cannot fully understand, but at least you get what I'm trying to say first, and then you can understand later. Get the right statement and then meditate on it. The real things you need to get the right statement. If you meditate on the wrong statement, then you will lost forever. Okay. Any question? Other question before? Lost. Simple lost. Simple luck, then lost already. And yeah, question. R prime t. R prime t, you have a path, right? Okay. You have a path. If you differentiate the path, you get the velocity. You get a velocity, meaning it is the tangent vector. Tangent vector to the path. Tangent vector to the path. Okay. So in this case here, this is a one-dimensional curve, right? One-dimensional, I mean, function of one variable, you know how to find the tangent, right? So these are the tangent. So r prime theta represents this slope of this tangent line. It's the dy dx if you want. Pi over 2, yeah. Yes, the tangent direction. Yes, tangent direction of my path. Correct. From the sphere. Let's bring this one up. Yes, it's that arrow. Because I'm trying to represent my x using this arrow here. So I'm opposite to this x axis. Make sense or not? So let me put the green arrow here. Okay. Better? Okay. Okay. I mean, max can be explicitly clear one if we want to make it rigorous and clear. Yeah.
So is this imply that the directional theorem? So it is directly imply that the directional direction is equally with the
Non-derivative is what's the question? No, I mean the gradient. Gradient is perpendicular to the. Okay, let me write the sentence down. So the key here is the gradient of delta f, sorry, big F is perpendicular to the tangent plane. Okay, tangent plane. If we talk about tangent plane, right, we need to talk about point. Okay, at point of the surface. Of what surface? Okay, the surface defined by fx, y, z equals to k. Okay, this is the full statement. The gradient. So the gradient. The gradient f. Okay, the gradient f. Yeah, the gradient. The gradient nebula f is perpendicular to the tangent plane at points of surface. What surface? F x y z equal to k. Okay, this sentence here only makes sense. Okay, delta f. What is the f? F is the surface when it is equal to k.
vector from the center to that point.
Always, not always, not always. I mean, not always. Depend on your surface. Not always. Yeah, in this case, yes, because 001 is the scalar multiple of 00. I mean 002 is a scalar multiple of 001. So it is true. Okay. I mean in general, depend on your delta F. Depend on your gradient. Okay. Question? Other question? Okay, so another thing is I'm more concerned of you how you understand subject matter. So no need to be too worried if I cannot finish my lecture because your class is still fine because your class is fully controlled by me. So I have some authority to stop where or include what I want based on the skeleton they give me. Okay, so I mean, I am more concerned with how you understand one subject because if you can understand one subject well, you can apply this method to other things. Okay, compare to you to learn a lot of new stuff, but you don't know what's going on. I think this is better. Okay, I prefer quality than quantity. Okay, because if I teach you this, okay, maybe I don't teach you the new subject. You also can read yourself already because you know what is going on inside. Okay, you get what I mean? Rather than you just get this question and then do it, get this question and do it. You don't know what is going on. Then I change another question, you also don't know how to do already. You get what I mean? Yeah. So when you do question, right, try and appreciate what's the question trying to get you to do. What's the concept they're trying to test you? Okay. So if you see the teacher, why can straight away change this question, change that question? Because they are playing around with the concept. Okay. So you need to get hold to the concept. Okay, I mean, it is hard. It is hard. I mean, nothing in this world is easy. Okay. So you need to put in effort. So that's why I ask you why you do it. So actually, why is the fuel for you to move forward. If you don't know why, you will easily stop somewhere. Okay. Okay. Question. How about we take a break and then we come back for multiple in the group? Okay. Yeah, let's take a break and then we come back for multiple in the group. project 呀。
要不要求是你原本是至少半页 A4 纸，
对，
就这个 A4 纸，就是跟我们刷那个 PDF，我们那个 PDF 多少页等于啥意思？
一样啊，就跟上次一样，你上次怎么决定一页半的？一样，跟上次。
就是我在 Teams 上给你发那个 PDF
啊，对。
那
我觉得还行，可以，大概那样子。
一页 PDF 就等于一页 A4。
OK，这样子，不然这样说，就是你那一整页嘛，充满字的版都要充满字，就这样。
就是从
那边
哦，
懂什么意思嘛？就你要怎么说呢？怎么说呢？OK 啊，用我自己的例子来看。就你不会想说要算那个台德的间隔吗？I mean，呀，等一下啊，
不是，就是我想确定我应该写几页，应该就是写几页。
就你怎么决定？你 Project One 我们不是也有页数的限定吗？对，我们不是有1.5个页数，现在只是调成0.5啊。
就是那个一开始的1.5页数我不是很清楚，然后我
你不是很清楚
对
？OK，你不是很清楚，可以，就大概就是充满大概这么多字哦，大概这样，就大概这样。比如说，你看一整页是怎么样，大概都可以到这里哦，差不多
这就是半页
啊，差不多半页，大概这么长，
这么长，
至少不够是吧？不够，
感觉没多少内容，
不够你没有，我说至少，我不是说最多，但是至少
最多一页。
最多，如果你真的没有办法超过1页，那就超一点吧。你写到2页，我觉得就太多了，你明白吗？你也讲不完这种东西，我觉得。对
就是这个 PDF 的页跟那个我在 Teams 上发的 PDF 是一样的。
差不多啊，差不多啊。如果我觉得你不够长，其实我会提醒你，这样你把它放多一点。但是如果还好就大概就这样，大致。I mean，I mean 我觉得这种东西不应该成为你的一个restriction 啊，就是说你要把你该写的东西写出来，就对。也，但是我只是说你不可以写到太短，就这样。我的意思是这样。
有这个问题。
也
所以呢，这个 gradient function 呢，不要管它那个 point 先啊。gradient function of x y z，这个 function 是个 plane 的。
不是，因为给了你一个 normal vector，你就会 define 一个 plane 了。plane 是由 normal vector define 的，所以这些是 normal vector，所以我给你一个 normal vector，你可以做出这个 plane。
所以这个 gradient 其实是 normal vector 的。
对，来，我这边写，刚才，
对，我刚才就是看，
这个
我刚才完全不要听这个，因为我怕我乱。
OK，
然后过后我就看这个。
对你先抓这句，
对，我是抓这句嘛。
你抓这句，然后你再。
所以你带进去就是其他的那个，你 x 要带进去，它就是那个 plane 上面的。
对，所以这个 gradient 给了一个 function of
normal
vectors 的 slope 也可以 ，slope 是你要拿到 number 才变 slope，不然就有方向。
那个 r prime t 是什么
？r prime t 啊，那刚才有人问哦 ，r prime t， 它是那个curve 的 velocity 吗？也是代表它的 tangent。那我画这边也是。
一个 report，然后那个 presentation 是用 B 的，这里
对呀，
给我做2个东西出来。
对，一页这样哦。
这样我觉得万那要写成 PDF，但是有讲什么时候要写成
Beamer 是 presentation 用的，
对，分2个，这2个。
一个是 presentation，一个是。
哎，我在想啊，这个r prime t 是不是一定会往 x y 的正方向
？x y 的正方向跑是什么意思哦？什么意思？
在讲什么？
你再讲一次，我不懂。
它的 r prime t 的 x 和 y 应该不会是负的。
在讲什么？
对啊，
没有，这是我选的 part， 不同 part 就有不同的东西啊。这 part 只是其中一个吧。呀，我选了这个 part， 这个 tangent 就定了。我选不同的 path，tangent 就变了。但是变来变去呢，这些 tangent vector 呢都活在那个 tangent plane 上面，它们一直都 perpendicular to 这个点，在这个点上面。
gradient vector 的它意义在哪？
gradient vector 的意义在哪里啊？
因为你看，为什么这一个题目，它的 gradient 它是
你要分开 gradient 跟 derivative 这2个概念，分开了吗？
这它 OK，gradient 到底是讲的什么？
呀 ，gradient 是什么？是不是 ？gradient 是什么啊 ？gradient 就是那个 partial by definition 啊 ，gradient 是那个 vector build out using 那个 partial derivative， 记得吗 ？definition of gradient 是这个。我们刚才讲了很多 gradient 的 interpretation， 但是它的 definition 呢是这个，你一定要回到 definition， 就是这个，这是它的 definition。
我是有看到这个，
对，就是这个。
我看哦，我问一些比较，
你问，
我们可以 visualize 它吗？就是它这个是表示什么？它就是
这个可以 visualize， 这个可以 visualize， 这个可以 visualize， 这个啊，你说怎样 visualize 它哈？好像我告诉你怎样 visualize。就是我们那个，对哦，真的没有错，我没有跟你开玩笑，是真的。这个
它就是怎么来
啊，就是真的，就是怎么来？为什么呢？为什么 ？OK， 可能你还不是很相信为什么？它的意义是这样，你看啊，你看，为什么还是 normal in general？in general 的话，你会有这个 equation。等下等我写完东西，再我再解释。 还有2分钟了。OK， 它的意义在这里，它的意义在这里，你看它的意义在这里，看到这个 gradient 在哪里吗？OK， 等一下等我写完之后我再解释给你。是零 ，OK。然后这个东西是什么？这个东西啊，我 parameterize 它上面的点，就是意思说我 consider 全部 curve 在上面啊，某一个 curve 也可以，各种各样的 curve 在这个 surface 上面，这个 t， 给我一个 t， 给我一个点，给我一个 t， 给我 xyz，OK。所以你看这个点上面的 derivative 是什么东西来的？它的 tangent 哦，它的 tangent to 那个 curve，
OK
啊，对不对？你看 tangent to 那个 curve 到我的 gradient 它是0，
到你的 gradient 它是0，所以它的 gradient 在这里的意思是 perpendicular of gradient。
对，所以我就说你要分开哪里这些 gradient 活在哪里，对啊，这个是 gradient of 我的大 F， 这是 gradient of 我的 curve， 对不对？所以你要分开 gradient of 什么啊？可以吗？
像这个 gradient 在这里的 definition 是这样，它的意义在哪里？
谁的意？
就是它比较 application on 什么？就是说我在数学上的话，就是他们要找出这个东西来定义它，是为了什么？
他一找到它，他就决定了一个 plane， 一个 vector 加一个点，你就有一个 plane 了。
OK，
我们的重点是这个 plane， 我们要找这个 plane 啊。
OK，
所以 OK 了，我这个 vector 我就可以造出这个 plane 了。所有的 curve 的 tangent vector 我都知道活在哪里。
所有的课的
tangent vector 活在呀。可以吗？
所以这样讲的话，我们其实是为了要找到那个 gradient of vector 才 imply 去就才找到那个 plane， 所以意思就是我们不能 directly 找那个 plane， 所以 before 找 plane 我们就要有这个东西。
对，因为一开始为什么一开始你讲找这个 tangent， 你一开始讲找 equation of plane
我明白你的意思了，现在我完全明白。OK， 知道，我懂为什么。OK， 明白。
OK， 好，可以。Hello， OK， let's start. Yeah, so yeah. Okay, so let's continue with this triple integral. So last time we stopped at triple integral. In triple integral, what is our domain? Our domain is R3. Okay, in R3, instead of integrating over rectangle, we integrate over boxes. Okay, we have 3 dimensions now. Okay, so boxes. So you get cut at x-axis delta x, y-axis delta y, or z direction delta z. Okay, there are 3 directions you can reduce. Okay, last time we mentioned about this. Okay, so this is the picture here. So you can add more partition at the direction of y, x first, or y first, or z first. Okay, and it is not different if f is continuous and your surface and your domain is a box. The Fubini's theorem tells you. Okay, so this is a one-dimensional higher version of our Fubini's theorem. Okay, should we skip this example or not? Or maybe I just let you see how we compute this, and then we won't do the computation. So how to compute this? Okay, so how we apply the theorem. So you want to do triple integral on this function. Okay, 3 variable function. So how to do? Okay, in principle, what you need to do, you need to know what is your B first. Okay, what's your domain? Always know your domain. Okay, always know your domain. So what's your domain here? Okay, your S is going from 0 to 1. Okay, your Y is going from, you need to draw your domain. Always need to draw your domain. This is a skill you need. -1 to 2 for Y. Okay, maybe let's use the other direction for Y. So we have -1 to 2. And then Z direction, we have 0 to 3. So what's our whole box here? Our box maybe looks something like this. Okay, so this is our box here. So let us move this box here, box here, box here, box here. Okay, so this is our box. So by Fubini's theorems, right? How do you compute the triple integral in this box? You can use the iterated integral. Okay, you can use the iterated integral. Okay, and then doesn't matter I differentiate, I integrate dx, dy, dz, or dy, dx, dz, or dz, dx, dy. Doesn't matter or not? No. Okay, Fubini's theorem tells you that they are all equal. Okay, this is what it means. Okay, no matter you do dz, dy, dx, or dy, dz, dx, or the others. Okay, right. Okay, so you can do any of them first. Okay, so let's do dx, dy, dz. Do you know why this is a concern or not? Do you know why is this a concern for this Fubini theorem here? Why? Okay, because changing the order might give you different answer. Okay, only when it is continuous and a box you can do it. Okay, because maybe changing the order will give you different answer. Okay, so in this case here we differentiate, integrate x first, so 0 to 1, -1 to 2, 0 to 3. Okay, so you do the iterated integral. So we won't proceed this calculation. I just tell you how to do it. Then you can try and build it. Yeah. Okay. Or anyone else have problem partial integrating this function or not? Does anyone have problem doing this? Anyone has problem? If you have problem, we can do it together. If not, we skip it. You have problem, huh? Okay. So let's do this. No problem. Let's do this. So when we partial integrate with respect to s, right? What do? We treat the other variable as a constant. Okay. So you integrate yz squared x, what do you get? What do you get? Exactly. Okay, you get this. So you integrate from 0 to 1. Okay, so what do you get? You get 1 over 2 yz squared. And similarly, you do for dy and dz. Okay. You want to continue? You want to continue? Okay, I'll let you continue. So what's the next? What's the next thing we get here? Okay, good. Evaluate for -1 to 2 dz, which is just 4. Okay, 4 over 4 is 1. So z squared plus or minus -1 over 4 z squared dz. Okay, and then this one we get 3 over 4 z squared dz. Okay, and then you continue. So this one is 3/4 divided by 3z from 0 to 3. Okay, so what do you get in the end? You get 27/4. Yeah, that's it. Okay. Very straightforward. Okay. So similarly, it's always it is always that we not dealing with so nice, the domains that is so nice, which is a box. Okay. We will deal with some other domain that changes based on our point. Okay, they are similar to our two variable case. Okay. Remember in two variable case, the y might be controlled by some x function, or the x will be controlled by the y function, right? Okay. So this is similar to three multiple integral. Okay. So first type of region. Okay. You can just look at the picture first. Okay. Just look at the picture first. So you might the value of z might be controlled by a two variable function now. Okay, it might be controlled by two variable function. Okay, not that this is still a domain. This is still domain. Don't confuse with graph. This is still a domain. Now our domain already upgrade already. Yeah, upgrade to 3 dimension. This is the problem. Okay, we cannot. So far cannot. You can try imagine and then tell us next time. Okay, so I mean, yeah, R4 for now we still can't imagine it. Okay, we can't imagine it fully.
This for future user.
What do you mean?
All the things we learn is for future user.
No. I mean, there's I mean, how to say? No. I mean, to say for how to say this? Future use. Okay, so one idea of mathematics, right? Okay, mathematics sometimes go advanced than physics most of the time. Okay, because we pursue mathematics subject as we like, or we just ask the question because we just generalize it, but we don't know what is the use of it. But later, maybe when physics get advanced, when they can see stuff, okay, maybe they can see smaller stuff, quantum stuff, or maybe they can see far stuff, and then they realize that there's something that is realizing the theory. Okay. Yeah. Okay. Yeah. So depend on what you say about using it. So I mean, we are using it now, but not sure is it useful for you, right? Okay. Yeah. So yeah. Okay. So one type of region is controlled by XY. Okay. The Z value is controlled by XY. Second is you have more control. Okay. Your Y axis is controlled by your X, and then your Z value is controlled by XY, both of them. Okay. I think this is not too important. Very important thing is how you see your domain get controlled by this. Okay. So I mean, one important thing here is the order, right? The order. Okay. So let's say you see the Y is controlled by X, and then your Z is controlled by X and Y. Can you switch order or not? Can you do something like this or not? Is it sensible to do something like this? Is it sensible to do something like this or not? Can I do this? So this is d y dz dx. Can I sort order? No. Can I sort order? No? Sort order here. Why not? Pigeon said cannot. Why not? The C, where's the C? The Z, okay, the Z is controlled by the Y. Uh-huh. Yeah, right. that's the point. That's the point. So your Z is controlled by your Y, but you already integrate over the Y. Okay, then what happened to the next Y? Okay, so you need to do it by order. Okay, so if your function is determined by X, you need to do the X last. Okay, so there's some order problem here. So you see, although I write here first, right, this integral is done last. You see the order difference here? Although I write integrate A from B first, but this is the integral that I done last. Okay, because why? Because all the other variable depend on the X I integrate. Okay, so I do it last. What do you mean by inverse? Inverse function? Oh, you mean, okay, you mean you want you to have inverse, or do you? I think I roughly get what you say, but what you say is wrong. I think I roughly get what you say, but what you say is wrong. I mean, yeah, we can talk about it later. I don't want to go into that case first. Okay, I want them to understand the thing you integrate last is the number that you determine, is the variable that determine the next variable. Yeah, this is what I want to say. The variable that you integrate. Okay, let me write down. The variable that you integrate later determine the variable that you integrate later determine the variable you integrate first. Okay. 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 So you see, because your uxy is controlled by x and y, so you integrate it over it first. Okay. Because your y is depending on your x, so you integrate it before integrating x. And then you integrate the whole thing. Okay. Okay. Is it okay? For this line here, you need to know. This line here. The variable that you integrate later determine the variable you integrate first. Okay. Does it make sense? Okay. How about I don't show you the formula and then I give you this. For example, I give you this. How to integrate, how to arrange the integral for this set here. Okay. So you can see that your y, okay, determined from C to D. But your x is fixed by y, okay? And then your z is fixed by x and x and y. So how you arrange your integral here? So what's the order you need to take? Let me ask. Okay, someone call you. So what's the order you want to take here?
The outside one is
Mm-hmm. Dx, huh? Okay, and then that. Okay, so let's put here. So the outer one is C to D, and then the inner one is H1, Y, and then the innermost is U1, XY, 2, U2, XY. Okay? Yeah. So let's compare. See? Okay. Yeah, good. Why? Because Z is determined by X and Y. And then x is determined by y. So you integrate y last. Okay, make sense? Yeah. So any question? Question or any question on this? Okay, if no question, right? Okay, so I let you try this. Okay, you try this for 5 minutes. See if you can do anything. Yeah, one very important technique you should have is people tell you one concept, right? You can strictly quickly work up an example. This is one of the technique you need to have. But in class, right, I will ask you to do it suddenly, but I will give you the answer later. So you need to train your instinct. Train your instinct. Develop your instinct. Develop your intuition. Okay, we say intuition. Develop your intuition. What's intuition? What's intuition? Wow, this is the first word, right? When I go study mathematics, the tutor keeps saying, use intuition, use intuition, use intuition. So what's intuition? The first one, first idea. I think roughly right. Yeah, the first idea, I mean, pop up in your mind when you get mentioned about the word. What's mathematics? What's mathematics? Mathematics, mathematics. What's mathematics? I feel like mathematics is truth. Truth to everything. Bible. When you use the word Bible, right? There's a lot of interpretation. Okay. I think mathematics is, I think, more than that. For me, at least for me. For me. Hey, where's Venus? Why I always don't see Venus for 2 days? I don't know. Wait, let me see. Yeah, last Friday I still saw her, but yeah, maybe I need to ask. Sheldon really gone already. Where's Sheldon?
Around the world.
Around the world. I think those who come now are quite consistent, and then those who don't come also quite consistent.
It's very good at this situation. Other agents not consistent one.
Oh, is it?
Yeah.
Okay. Okay, let's discuss. So let's discuss how we work this out. So we differentiate the function z, okay, with respect to this solid tetrahedron, okay, bounded by the plane x plus y plus z equals to 1, and then x equals 0, and y equals 0, z equals 0. Okay. So what is x plus z, y plus z equals to 1? How does this plane look like? What's the normal vector here? 1, 1, 1. Okay, the normal vector here is 1, 1, 1. So this normal vector is 1, 1, 1. So meaning this is a slanted plane because it's normal to that plane, right? Okay. So in particular, we have this drawn here. So this shows you the intersection between z-axis, x-axis, and y-axis. Okay. So this is the plane. You can infinitely extend it, this plane. And then x equals 0 is the innermost plane, and then y equals 0 is, where is it? Wait, s equals 0 is what? S equals 0 is this plane actually. So okay, let me write down. So s equals 0 is zy plane. Okay, y equals 0 is zx plane, xz plane, whatever you want to call it. And then z equals 0 is xy plane. Okay, so far okay. 首先 got problem reading this equation or not? Wait, can you can you read this equation and find the plane? All of them. Can you? Because last time I remember you have problem reading the cylinder equation, right? Yeah, so do you have problem reading the plane equation or not? Nothing. It's okay, it's okay, it's okay, it's nothing. But I already tell you something. Have you accepted it? No, I mean, have you accepted my answer? Huh? Have you accepted? I mean, yeah. You cannot catch me. Cannot catch me. Okay. So does anyone else have the same problem or not? Or others can get it? Others can get it or some of you also cannot get it. Like x equals 0, why is it the zy plane? Some of you got it, but anyone don't get it? So x equals 0, right? X equals 0. So what happened to, for example, right? Okay, if only Zhexian don't know, maybe we skip this first. Then I can talk to you individually. Okay. Or some others also cannot get how to get a plane. No response is good or yes, good or no. Okay. Okay, maybe we'll skip this first. If you don't understand, right? So take the word, these are the xy plane, zx plane, and xy plane first. Okay. So we skip the logic going from the equation to plane first. So you need to start with this plane here. So intersection of this plane. Okay. So what kind of order you can take here? What sort of order you can take? Anyone try any order or not? X, Y, Z. So you mean dx, dy, dz? Dx, dy, dz. Sure. This is not the answer in my lecture note, but let's work this out. So dx, dy, dz, meaning what? X depend on y, might depend on y, and y might depend on z. I mean, x might depend on y and z, and y might depend on z. Okay. So this means that it's better we fix z first. Okay. Let's find what's z first. So what's z? Z is going from where to where? Okay, from this picture, we know it is 0 to 1. So in general, how to find it? In general, how to find it? So the bottom part, you are cut out with xy plane. So when it is xy plane, that equals to 0. Okay, and then how you find the top value? Okay, then you need to know how this plane gets slanted, really. Yeah, so this is a 1, 1, 1 here. Okay, so you can see that this plane is increasing from z equals 0. So the highest point is the, is it? Can it be? Yeah, it is the intersection between z-axis, because the other side also cut off by the other two planes. Okay, I'm talking to you from a viewpoint that I don't know this diagram at first. If I give you this diagram already, I think it's quite obvious what you need to do. Okay, so so the highest point is the lowest. Okay, let me hold on. So the lowest is xy achieved at xy plane where z equals 0, and then the highest z, the lowest z, the highest z, is when what? When xy equal to 0. When x, and which is z equals to 1. Okay, so you go from 0 to 1. So how about how you decide dy? How y changes? 0 to negative. Huh? Negative z. Okay, z. So how you decide this? So you want to look at the change of y. Okay, so you fix z. Okay, you fix z. Then you want to look at the change of y. Right. So what's this line here in particular? Huh? What's that line? What's that line? Y equals to negative z. How do you find this? Wait. Hey, the answer is coming from Mingxiu, right? You agree with Ziqian, what Ziqian said? Oh, you're looking at the graph. Okay. So so what? So the answer is y. What's this y? Equals minus z. You say minus z. You say minus z plus 1. Okay. So minus z or minus z plus 1. So there are two things here. Okay. So how do you decide this? So in this direction here, how do you find this line? You know how to find this line? This line lies on what plane? Huh? What plane? X equals 0. Okay. So you need to let this surface here equal to x equals 0. Okay. So when x equals 0, what happened to my surface? So meaning you cut your surface at x equals 0. So what do you get? What do you get? You substitute x equals 0 to this equation. Sayed, what do you get? Hey, don't tell him. Don't tell him. Huh? What sleep? Translate. Never mind, let him talk to me. He cannot bring you forever, right? So when you substitute x equals 0 to the equation, what do you get? Let him deal with it. Yeah, you see, he know 1 minus y. Okay. So when it is 1, z equals to 1 minus y, that means my y is going to be minus 1 minus z. Okay, so this is 1 minus z. Okay, so meaning what? Meaning what? So apply the same principle. If I fix a z, okay, I go from y equals 0 to this line. Go from y equals 0 to this line. Go to y equals 0 to this line. Okay, so all my y at each cross section is bounded by y equals to 0 and y equals to minus z plus 1. Make sense? Make sense or not? Okay. Okay. So this one is minus z plus 1. Z plus 1. Okay, how about the next? How about the next? So you already integrate everything cut off by 0, cut off by y, cut off by z, cut off by y. So what's your x? Your x is what? Y 1 minus z minus y from 0. Okay, 0. Correct. Yeah. Can picture now. Okay, so how to picture? You see, so if I cut at z, right, I got this line. Okay, but in the end, what do you have? You actually have some things that looks like. Let me draw if I'm okay with the drawing. So you draw something like this. Top. Hey, wait. I think, what am I doing? Okay, like this. Correct. Yeah. Okay. So you see, so you are integrate the first two integral you have done a cross section. Okay. And then the last integral, you need to include all these pieces. Okay, you need to include these pieces in. See the idea or not? See the idea? The idea I taught at first. Dot become lines, line becomes surface. Okay. So what is this? Dot with line. Okay. After you have this triangle, put all the triangle together. And then you get this whole solid here. Okay. This is the idea keep popping up. Tetrahedron. Yes, this is a tetrahedron. I draw like pyramid. The base is triangle. Yeah, that's why I think something wrong with my drawing. Yeah, so what's wrong with my drawing?
Base is triangle.
The base is triangle. So what should I do? Oh, I know what should I do. Okay, let's get rid of this. Okay, so this one like this. Yeah, maybe I draw the extra edge as the behind one, so got more. Okay, yeah. But you see, this Z here, this Z has nothing to do with this picture. This Z is living in the other dimension. Okay. So this is the domain, just the domain, only the domain. This is just the domain, not the whole graph. Okay. Okay. We will skip this calculation. Okay, we skip this calculation because just now already do one example of iterated integral. Yes. What's the answer? You already computed, is it? Okay, I can give the final answer. Is 1/24. Okay, make sure stop. Okay, yeah, the final answer is 1/24. You can check. Okay. Do you all use, what do you use? dx, dy, dz or what? Oh, okay. Yeah. Yeah, you guys should try different direction. Try different direction. Okay. Yeah, try different direction. The notes here have dx, dz, dy, dx, but they are all similar in this case here. They are all similar because tetrahedral, you look for different way also tetrahedral. Just the variable change. You can try out, change the order and then try it. And try it. You should try it. You should experiment yourself. So for maths, right, it's important that you can experiment things. Okay, try with different order. Because try with different order, you can see more insight. This is where you get intuition. Intuition, for me, for my understanding, so for intuition, you want to gain intuition, right? You need to see something. Okay, you need to see something. You need to see. You need to feel. You need to observe. Okay. Don't wait for people to tell you. You need to observe yourself. Observe the nature or observe the surrounding to get intuition. Okay, observe. Okay, let's skip some of the example. Let's talk about some idea first, and then next time maybe we'll do example. Okay, so let's talk about idea, then next time we'll do example. So in triple integral, we can do it in cylindrical coordinate. So as last time I said, you can fill our R3 using cylinder. Okay, if I fill my R3 using cylinder, the change of coordinate we'll use is x equal to r cos theta, y equals to r sin theta, and z equals to z. You know what this means here? So I change my xy into polar coordinate. Okay, I change my xy to polar coordinate. So the R2, I can fill it with all the circle. Okay, and then how do you fill R3? What is the difference between R2 and R3? Infinitely many R2 you have. Okay, then we just put all the circle Z. Okay, we just put all the circle Z. Okay, to fill out all the spaces. So this is the change of variable that you need to satisfy. Okay. Okay, let's talk about idea first, and then next time we will do example. And then in triple integral of cylinder coordinates, we also can have this kind of a region, controlling region by function. Okay, in this case, we have Z, theta, and radius. Okay, these are the three. So the key point here, right? So the key point here, you need to note here is from three-dimensional, we change to what? Three coordinates. Okay, we change it to r, theta, and z. Okay? We change to r, theta, and z. So it is three-dimensional. You cannot change it just to two-dimensional or one-dimensional because this is not a one-to-one or one-to map. Okay, three-dimensional stuff still have to be controlled by three-dimensional variable. Okay, in this case here, we make it into radius, angle, and height. Okay, okay, this is the key point. And then here is the formula we have. Okay, and then so this one is the same concept. Then the next concept is spherical coordinate. Okay, why we place this as a later section? Because you can see that this equation is harder. Okay, why is it harder? So the idea of spherical coordinates, right? Okay, so okay, let me draw things. So you have an R3 point. You need to tell me instead of sphere, you need instead of circle, you need to tell me which sphere it lies on. Right? You need to tell me which sphere. So you need to find a sphere equation on the center at the origin with radius r. Okay, so let's see if this is true. Okay, I say there's one manifold you cannot forget. Okay, going out from this class, what's the manifold? Sphere is the sphere. Okay, let's see if these points represent a point on the sphere or not. Okay, so let's take x squared plus y squared plus z squared. Is it equal to some radius r squared? R or r squared? Yeah, r squared. Let's make it r squared radius. So this is a sphere centered at the origin with radius r. So let's see if this is true. Okay, how many variables we have here? Did you notice? How many variables? Three variables. What are the three variables? Rho, phi, and theta. So what are these variables referring to? Okay, so rho is the radius, and then phi is the angle from the z-axis, and then theta is the angle from the y-axis. Okay, so what do we have here? So radius is greater or equal to 0. Phi is in between minus pi over 2 to pi over 2. Okay, theta is in between 2 pi and 0. Okay, So this set of data enough to explain everything in R3. Okay, can you see or not? Can you see it? So let's start with which one? Start with this one maybe. Start with the theta. Okay, theta tells you what's the angle on the plane. Make sense? Okay, and then phi tells you what's the elevation from this plane. Okay, right. So you can see that with this elevation, with this revolution, you will get a sphere. Okay, but you need to fill the whole space. So you need to be able to increase the radius. So you take all radius. Make sense? Does it make sense why we only take pi over 2 to pi over 2 for phi? We don't take the whole circle because it can be done by theta. Right? If I go to the other side, meaning I can take theta, go to the other side, and then I fill that space. Make sense? Huh? Okay, so now prove that this actually is a point on a sphere. Okay, so let's prove it. So x squared is r sine b cos theta squared plus y is r sine phi sine theta squared plus rho cos phi squared. Okay, so what are these? So these are just phi squared, sine squared, cos squared, theta plus phi squared, sine squared, sine theta squared plus rho squared cos phi squared. Okay, so you can see that you can factorize the sine square phi. Okay, and then combine sine square theta and cos square theta. So cos square theta plus sine square theta is 1. So I get rho square sine square phi plus rho square cos square phi, which is in turn rho square. Okay. Okay. Yeah. Okay. So I mean, there's something you can play around with, right? You can swap this cos with this sine also can. Then it just result in what's the order you read this elevation. Okay. Any question? I introduced up to this part here because this thing will be useful for your assignment. But next time we will do some example. Okay, any question before we wrap off? Okay, if not, you also can try some example, but next time we will do it together. Okay, see you next